Okay, let's see if I can do this. Okay, so you can hear me, right? So I'm just not going to record this because my machine is not going on to the web. Okay. Okay, so what I was trying to get you to think about is that, so we were talking about this particular reflex agents, right? So I was just saying that you may be able to write condition action rules with respect to the state. So you're getting the sensor information, and you're trying to figure out what the world is like right now, and then the rules will tell you if the world is like this, you should do this action, and that's what you're trying to do. So my question is, what would you say are the kinds of rules you would write if it is a car, an autonomous? Okay.
I would say one of those, make one like
Okay. But the problem, so what, any others? Yeah? Okay, fine. Do people see a problem with these kinds of rules? Yeah?
There might be like exceptions, like if someone's running a red light.
So that's one kind of a problem, but there are other kinds of problems. I'm looking at a slightly different kind of a problem. Who is giving you, so whatever you are looking at the environment, what do you think the car gets in its sensors? What do you think the car gets? Yes, go ahead.
Yeah, the car will just get like pixel data or whatever, but probably not actually translated to the code out.
This is what I'm saying. So this is a huge interface issue. In general, this is something that we are stuck with in AI. The sensor, it's not always the case. In, for example, if the domain you are in is something like driving, then it really is the case that you will be getting basically the raw pixels. Okay? If on the other hand, the domain is, let's say, a web shopping engine, right? Then the inputs would be pretty reasonably structured inputs about database records and information about sale and so on and so forth. Do you guys get that? Okay. For the web shopping kind of things, you can actually write condition action rules saying if this thing is less than 10% of its average price, and if my budget allows it, buy it. That's a reasonable thing to do. Right? Whereas for something like the car scenario, for something basically the basic day-to-day kind of scenarios that we deal with, we are stuck with this problem of what we would call pixels to predicates. Actually, I think I need to do one thing here. will also record it. Just in case I want that. So, the offline, disconnect the internet. Okay. So, with my pen. I'll just show it. I have the pens here. Right. I just left the pen somewhere. The one that writing. It could also happen. So that would be hard to write on that. So anyway, this issue, as I'll be looking for the pen, this issue of converting the sensory information into things okay, like this. I think I will. Yeah. I guess I need to be saying, but let me continue. Is this issue of getting from sensors to conditions is basically called the pixels to predicates problem. Okay, pixels to predicates problem. That's just a shorthand notation for it. So the idea being that let me actually just connect this. I'll be out for a second. Okay. Yeah, I don't think this. So no, that's it. That's fine. So it's called the pixels to predicate problem, and that reason is that the things that you get to write yourself, you tend to think of the world in terms of objects, in terms of relations, in terms of concepts. What you are getting oftentimes from the world is unfortunately not that. It is like pixels, it's signals. Okay, so when I said last time around that, well, these condition action rules can be represented some sort of a network. So in some sense, this network is taking as its input what? If it was in terms of concepts, then it is taking inputs, okay, there is a pedestrian in the intersection, there is another car in the other lane, and so on and so forth. And then comes the action that is the right action to do. If on the other hand, it is actually only getting the pixel information, then you have this tricky problem, which is how do you convert the sensory information into things that we understand, like objects, like relations. We take this for granted. We do this, from the as when we were kids, we've been able to do that. So the question is, how do we do that for the machine? And the idea there, yeah, okay, I actually got it. The idea there is that you may have to convert the images into some sort of an object relational representation. That's one idea. Okay? Let me try to get this in. I'm sorry for this has been a cursed day today, so we'll get through this. In my yes, please. Okay. Okay. But on the other hand, the advantage of today is that I might be chasing, so I might not be running around, and so maybe you will make sense of what I'm saying. Okay, we'll figure that out. So this, interestingly enough, this is a talk that I just was listening to, there is a conference on International Joint Conference on AI that's going on just right now. Okay, it's one of the oldest conferences in AI. It's the first one. Its first edition was started in 1969. Okay. Anyway, so it's being held online, and then I was just listening to this talk. This is Fei Li, and she was giving her talk. She's the one actually behind this thing called Imagenet that some of you may have heard about. And then she's giving a talk, and I just copied a slide. In essence, part of her life has been trying to do vision, to do object recognition. In the beginning, Imagenet kind of things would say, oh, there's a dog, there's a cat, etc. But that's not enough. You need to look at the picture, and you should be able to see the connection between all the objects. That's the way we see pictures. So her point here is that we will see this not just as there's a man, there's a woman, but there's a man, there's a woman is feeding man cake and all sorts of other things, and then the man is to the left of the picture and the woman is to the right of the picture, and all this other stuff that you essentially have. And if you have this vocabulary, then you can write the condition action rules, right? Because this is the language you think about for driving. Do you guys understand where I'm getting? Okay. So the question of how do you go from here to here would be the quote-unquote pixels to predicates problem. And as you may have read in the things that I made you read before the class started, it is a question of which piece that whenever there's a hard problem, the way researchers do it is they'll say, well, I'll forget about this part, I'll work on this part first. And I'll come back and work on this. And somebody else will say, no, I'll work on this part, I'll forget about that part. And I'll come back and work on this later. And the researchers now have two very different fields. One which basically assumes that they can write these if-then rules and then focus on the inference. And the others who assume we'll just look at the pixels or the voice signals and figure out what objects are actually present in the picture and what their connections is, etc. And then hope that later on at some point of time we'll connect it to actual doing this. Okay, depending on the place you came from, in general, you would have either picked to one side or the other side, and I just wanted you to kind of keep this in mind, because this sort of distinguishes, as I'll see, we'll talk about a little more in a minute, there's like a schism in AI community right now. Okay, some people basically think we should be going, for the longest time, actually, that the way the textbook is written, for example, is it assumes that somebody will take care of pixels and predicates problem. And so I will focus on the inference part. And of course, this is the dumbest agent architecture. The next one will be better. The next one will be better. But all of them, the question is who is writing the boxes? How is the knowledge in the boxes? How is the information in the boxes coming? So one idea is, of course, as I said in that next slide, that there is this intermediate layer. Maybe Fei Li will come with her system. It looks at the image and then converts it into some sort of a symbolic representation that you can use. And then you write your knowledge about the domain in the symbolic representation. And the word symbolic is essentially what you are doing. Whenever I ask you, you never seem to say, when I ask you, can you give me some rules about the cars, driving? None of you said things like, when the 14th to 19th pixels have less than the following amount of grayness, and the 28th to 99th pixels are, changed from the previous, frame by this much intensity, then you should do this. You never said that. Unless you think that way. You clearly, in some sense, thinking that way because your brain is processing all of it, but your conscious brain thinks in terms of concepts, in terms of objects, in terms of relations, in terms of symbols, which is why we think in terms of logic. To the extent we understand explicitly how any domain works, it would be symbolic. So this was the distinction I was making in the original readings that I asked you to do between the tacit versus explicit knowledge. You know, there are tasks for which you not only can you do them, but you know how you do them. You have a theory. There are tasks which you do, but you have no idea how you do them. If I ask you how do you walk, you say, I'll just show you this is how I walk. Exactly how are you walking? How much pressure are you putting in this joint? How much force are you putting in this other ligament? All of these are important to be able to walk. If I make you think like that, you'll fall down, right? Because you just over this thing. So this is all happening in the subconscious level for you. This also basically leads to, this whole discussion leads you also to system 1 versus system 2, which we'll again talk a little bit in the class today, but system 1, think of it as the subconscious brain. Okay, by the way, system 1, system 2 are hypotheses. People just hypothesize that human brain, not people actually, Kahneman, you know, one guy, he's a Nobel Prize winner, so you take care of whatever he says. You listen to what he says. And he basically said it makes sense to understand brain in terms of quick reflexive behavior and deliberate behavior. And the system 1 is the subconscious reflexive behavior. System 2 is the deliberate behavior. So if you see something and start running, that's system 1. Do you see what I'm saying? I mean, so if you, the reason you are insulting tiger by running away from it is because your system 1 told you that anything which looks like a tiger, run. Okay? And system 2 kind of does deliberative decision. Maybe after a while you can stop and say, okay, maybe I made the tiger unhappy by sort of insulting it by running away from it. Oh, it's too late now. Let's forget about it. That is system 2. Much of human civilization has been about system 2. There is nothing written about system 1. You know, books are about system 2. Language, codified language of all kinds is about system 2. Do you understand what I'm saying? Right? So, one of the interesting questions then is that if you were to, let's see, where am I? If I'm doing it this way, in some sense, I am agreeing to convert the world into language that makes sense to human system 2. And then the advantage of that is that humans tend to write the rules for the worlds for which they have rules in these kinds of concepts. Okay? Now this whole thing actually can be ignored if in fact, as I said, the input itself is coming as sort of structured data, like as in web bots or something. Because there, in some sense, it's already been, that world state has already been split into features for you to easily deal with. Whereas normal world just comes at you as pixels and audio signals. So if you do it this way, then this is you're doing actually converting the world into a language that makes sense to humans. This is what Pepe was talking about this morning. Then you can connect it to whatever we know about the world. So the question of who writes these boxes, well, I can still write these boxes. I can still write the box here, as long as the sensors to what the world is like right now is done by a scene graph or something. A different way is to say, to help with it, what you want to know is what is the action to do. Why don't I just make this whole thing into a black box? And it just gets the pixels, it does an action. Do you understand what I'm saying? Because no, the interesting thing is that as we're going from here, originally this was a black box, and we started putting structure in the black box. We're putting more and more boxes in the black box, so that we have something to talk about in the course. Another way is we'll all take a holiday. We'll just say, okay, tell me what your task is. And you say my task is, doing the right action for driving. And I'll just say, okay, here's the black box. This takes the pixels and does that. How did you get it? Well, that's a different question. I probably saw lots of examples of the state information in pixels. The car did an action, and maybe the car got dinged, so it said that's not a good action. It did another action, it wasn't dinged, so it thought it was a good action. So it learned by trial and error. But when it learned this way, it's just learning directly how to go from pixels or signals to action. Do you understand what I'm saying? So that idea would be basically, when you're doing that, you would be essentially saying you are doing end-to-end learning. End-to-end learning. So if you do end-to-end learning, there's no boxes inside the box. It's just one box. Give me your input, I'll give you the output. How do you figure this out? Well, I'll assume that you gave me a gazillion input-output combinations before, and then I'll try to sort of figure out which input makes sense for which output makes sense for which input. I'll just do it. Do you see what I'm saying? That is another way, and if you actually do it that way, and for a while people were just pushing it to go only in that direction. And if you do it that way, really only thing that matters is learning. And a whole bunch of data, or time for the agent to try, fail. So, this is where nice things like we'll talk about the types of environments in a minute, but one of the things is ergodicity of the environment. Very fancy word, ergodicity of the environment. An ergodic environment means from every state in the environment, you can reach any other state by doing some actions. Is life ergodic? I mean, by the way, if you want to, kind of impress people outside of AI, you should use ergodicity every once in a while. Because they will have no idea and you sound very smart. Ergodic essentially just means that the probability that basically you can go from any state to any state by doing some actions, some sequence of actions. Walking around this room, is this an ergodic environment? If I'm here and I want it to be there, I can walk there. If I'm there, I want it to be there, I can walk there. Any pair of states where one state Rav is, another state Rav needs to be, that's ergodic. I mean, I can go, so it's ergodic. So in the case of ergodic environments, I can try actions, see if they work or not, and if they don't work, I'll try some other action. Either which way, I don't die. I kind of gave it away. Is life ergodic? Why?
Can't be a baby again.
Oh, okay, that's the only problem you have? No, my problem is that you die. Death is a one-way trapdoor. Unless you believe in some nonsensical mythology of kind X or kind Y, death is the end. Right? So if you are in the dead state and you want to be in seeing a movie and enjoying your evening state, no, you can't do it. Right? Once you got into the dead state, you're dead. You can't come out of it. Most real worlds have dead states. If a car is going, And it says, okay, maybe looks like the right action to do here is veer strongly right, and it falls off it crashes the railings and falls off into the valley. At that point, it says, no, I think next time I should just do this other thing. There is no next time. The car is dead. Just like people, cars can be dead too. Some of you don't realize this because you played Grand Theft Auto. Right? Because you get up, you start, you get up, you start. Real world guys are not like that. How many of you haven't yet started driving but have already thought we know driving because we have played Grand Theft Auto? One big difference. When you're dead, in real world, you're dead. Not like Grand Theft Auto. The reason I bring this all up is Grand Theft Auto is a simulation. So it sort of makes real world into an ergodic world, even though it wasn't originally an ergodic world. So if the world is not ergodic, you can't do trial and error based learning. Because you can die. And the reason we don't die prematurely, remember, our babies, human babies seem to be living longer and longer as time goes on. Part of the reason is we don't just leave the babies in the forest and say, fend for yourself. You make a mistake, you die, that's okay. No, we just carefully construct very cushy living room with no guns, if you have any sense, and no huge bombs, and no open fire pits in the living room. So that little stretch of the world has been made ergodic. Modular exogenous events, of course, if an entire big asteroid falls on the home, all bets are off again. But with respect to what you made sure that this house, this little living room is ergodic until the junior knows how to deal with real non-ergodic worlds. Okay? So these are things that you have to keep in mind in terms of trying to decide, should I be going for approaches where I will write all these boxes, the box like condition action rules, what my actions do, how the world evolves, what is the state of the world. These things can be written by the programmers, can be written by programmers in terms of concepts that can be extracted from the real world, which is what that scene graph idea is. Or you say, to heck with the programmers, I'll get a huge amount of data and figure out how to do it, which is end-to-end learning. So the problem with end-to-end learning, that of course, if end-to-end learning works, right? Things are great, because why do we need all these other boxes we are done today? We basically say, for the rest of the semester, get more data, train, and then you'll have an AI. It works in some cases, but what are the downsides? One is, of course, you may not be able to learn because the world might be non-ergodic. But what are the other downsides? Yes? Well, I don't know what does it mean to say biases.
Inherent biases have to be certain things, like data says that you do things in this way, which may not be efficient or correct. Like we were talking about, how GPT-3 doesn't care about whether it's saying something racist or not, but it's learning it because it sees that.
Yeah, I mean, I guess bias, of course, I see bias as a much later emergent problem. In fact, what stops a random engineer from writing biased rules in the condition action rules? Remember, less than 40 years back, US judicial system was explicitly racist. We wrote into, not 100 years back, okay? We wrote into the Constitution bunch of racist things. This is not that we were just doing it, reflexively. We just said certain types of people are 3/5 the worth of certain other type of people. We deliberately using system to decide it. So yes, I can be biased by the engineer being biased too, the writer being biased too. The Dred Scott decision was made by a Supreme Court justice who was using system 2. I mean, if there is one place in the world where system 1 has no place and only system 2 is welcome, that is Supreme Court, right? You don't feel like, you look kind of questionable, I'll send you this way. That's not allowed in judicial decisions. Okay? So yeah, so biases can happen, biases can also happen this way, but here can happen inadvertently, is what you're saying. Here it is deliberate. Somebody actually sat down and wrote it. What else? Yes? What? What does it mean?
Like if you collect data from a supermarket in the morning, you're going to get answers that are more representative of the whole population.
Yeah, no, I think those are, I mean, you could say that that sort of a thing exists also for human data. So the condition action rules have to be separate for the morning and separate for the evening. If the programmer was not careful, you can get into those troubles there too. One big issue is basically what is called interpretability, contestability. Okay? Interpretability and contestability. So the idea there is that suppose I were to give you a judicial system which has sort of checked for the last 100 years, it just seems to be putting the right people, out of jail and the right people in jail, and the criminals in jail and non-criminals, go free. But they never explain why they did that. It's like a black box decision. Right? If you have that kind of a scenario, then when the decision made by the system is wrong, humans in the loop really don't have much of a hope of figuring out why the system made the wrong decision. Because this way of looking at the picture into these concepts is our way of looking at the world. Is our way of looking at the world. A machine doesn't have to, if it is being trained end to end and is learning its own ways of making sense of the pixels. These would be then, in those kinds of cases, you would say that machine is learning representations. And the representation that is learning, you can think of, if this is like the network, input is being fed here, output is coming out here. You can argue that whatever is happening in this middle layer is some kind of a representation of the reality that this system constructed internally. It's helping it in ensuring that the learning performance is good. But you don't know how to make sense of the system decision. You people in the... Now, here's an interesting thing. You can argue that maybe I don't need to know. Maybe if you give me a guarantee that this system will never do bad things, I'll just trust it. Like, how many of you really know how planes work? Why are you flying? Why aren't you asking the pilot, okay, what are you doing right now? Can you tell me? I really need to know. I mean, I'm not really sure about your, So clearly there are certain cases where you do expect some sort of a transparency for the decisions. Things that you trust, probably you don't need the transparency. How did you get the trust? That's a very interesting question. Like basically as to why we believe that the planes work and why some of us seem to believe vaccines don't work. It's a strange reality that we live in, right? We basically just looked at whatever things that we read and we said, looks like the planes aren't falling, I will trust the planes know what the planes are doing, the planes and pilots are doing. It's not just by intimation. Like in an authoritarian world, people can just say, we will change your mind such that now onwards you will believe that, planes are trustworthy. Trust has to be earned. And different people trust different things. It's a pretty complex situation. We are actually going through that right now in our own society. But the point is, you do not, in at least some cases, you expect that the explanation for the decisions is provided, that the reason for the decision is provided. If the decisions were made in terms of this, then the system will say, yeah, I decided, for example, it is the woman that is feeding the man because, look, I can see that it's closer to the man's mouth and the woman's hands are closer to the man's mouth. These are very discussed things. What if the machine doesn't actually, just because you wind up doing the same decision, the same correct decision for the same input, doesn't mean that your internal representations have to be the same. Strangely enough, they seem to be sort of similar for us, and it turns out for machines it's not at all the case. In fact, I wish I had, maybe I can show this. How many of you have seen this great, the school bus ostrich picture? I think I put it in one of the things. So I wish I can show it to you. Can you pull that up on the school bus ostrich? Because I'm not still not on internet. So basically, what happens is there is a picture of a yellow school bus, and the state-of-the-art recognition systems will say it's a school bus with, let's say, 86% accuracy. That we are confident that it's a school bus with 86%. Then I add some noise to the school bus. I, the adversary. It looks to all of us just like school bus. There is no difference because the noise that I added is changing pixel 14 by a little bit, pixel 95 by a little bit, adding some extra value for pixel 27, etc. I did it very carefully. I am a devious adversary. Out comes a school bus, which for all new people looks exactly like a school bus. But most systems trained on Imagenet basically will say it's an ostrich. Not only will they say it's an ostrich, they will say it's an ostrich with 99% accuracy. So the original school bus, I'm only confident that it's a school bus with 86%. But this other thing which just looks like school bus, I'm damn sure that it is an ostrich with 99% accuracy. Can you show this? Okay. I don't know if you guys can show this. Basically, like this is a slide from me. I mean, I'll pass this around. He doesn't need his thing, but so there's a school bus. There's another school bus. It turns out the second school bus, many systems will say is actually an ostrich. You can't, for the life of you, figure out why the second one is an ostrich and the first one is a school bus. Okay? You notice that people make, you can pass it along and then get back to it. Notice that people make mistakes, visual fallacies, etc., but they can understand the fallacies after they explain to them. This one, even though I told you that the second one is an ostrich, if any of you start seeing an ostrich in the second one, please let me know. Because you are a robot in the wrong class. Because I haven't found anybody who sees the second one as an ostrich, even though every state-of-the-art vision system sees it as an ostrich. That is your interpretability problem in a nutshell. Because most of the time, normal school buses are seen as school buses. This carefully modified school bus, you guys still think it's a school bus, but it's an adversarial example for the machine. And in those kinds of cases, not having a common vocabulary winds up being a huge problem. Okay? Yeah. So the agent architecture that we were talking about towards the end of last class, basically the more interesting agent architecture essentially also involves the goals, and the system sort of figures out how to put together actions given the state information and given its goals, instead of having one size fits all condition action rules. And that's what we will focus on. Okay? Yes, go ahead.
Why do we, with this whole predicate problem, why are we trying to adapt AI to use the sensors that we have to recognize them? Like we recognize that a school bus is a school bus because we painted it yellow and gave it a certain look. Why does the AI have to adapt to things that we made for ourselves and not have its own dedicated system? Because intelligence is not just looking at something.
So where is AI going to sit around? With you around or on Mars? What?
Probably with me around.
So, and do you want to be relevant in this new world you are constructing or not?
But it's exactly the same thing as like making an aircraft like a bird.
No, I understand. But what I'm saying is, in fact, first of all, there is a good reason to say that the kinds of sensors we have are pretty good sensors. Although we are always learning new sensors, the ones that we don't have. Obviously, we have infrared sensors that we don't see, with our own eyes. But I think it is useful for me and you to communicate. You need to at least see the things that I see. And I'm assuming that whenever there's a human and AI in the equation, human trumps AI. In the sense, it's the life of the human that I want to make easy, not the life of the machine. Machines are dime a dozen. Right? And so it seems to me that even if it is using additional sensors, it needs to still make sense of what I am seeing. So that, like for example, to be able to put itself in your shoes, which is one of the things, I think I mentioned the Salian test in the very first class, which is our ability to have mental models of others that you're interacting with. For AI system to have mental model of you, it needs to have a sense of how you see the world. Even if in fact there are better ways of seeing the world. Do you understand what I'm saying? So it again depends on the level of generality that you want for this AI system. If it is a very dedicated system that's out on Mars doing something, and only like 3 people with the right expertise need to understand what the damn thing is doing, yeah, use whatever is the best sensors, and it doesn't need to make sense to the humans. Experts have walked into the world of this machine, and they understand what is happening. But a household robot, that's not a good idea. Okay. Any other questions? Okay. So in terms of the course that we are going to be doing, I think part of which will start today. So essentially, if you are putting, let me see. Yeah, let me first actually do this. This is basically, I'm just repeating what I already said. Who fills or builds these various boxes? How the world evolves, what my actions do, how good is the world from my perspective in terms of my performance metric perspective. Who fills those boxes? As I said, you can have a modeling approach where the AI programmer populates the boxes. And then much of what you would be doing as part of the course is to figure out how to combine these boxes together to do the action. This is typically called inference or reasoning. That means I've been given the knowledge and you just need to do the right decision. Okay? The other is learning approach where the agent learns everything it needs, and it might either fill the boxes or ignore all the boxes and just go end to end from the input to the decision. And there is as I tried to explain to you, there is a major right now, as you come into AI right now, if it's 10 years back, this wasn't there. 10 years back, this approach was very much dominant. Right now, both these approaches are sort of almost, it's not clear which one will finally win. Certain things like for tacit knowledge, learning approaches are the ones that are working the best. Except even for the learning approaches, I want you to understand the distinction between learning to speak human language versus learning to just decide correctly, which is end-to-end. If I just do the right decision, do you need to know how I did the right decision? In some cases we do. In some cases we might want the decisions to be interpreted. Just a second. Okay, yeah, I'll get it. So this hybrid, basically when I say hybrid, essentially it's a kind of thing where you might use learning techniques to first of all convert the sensory information to object relational graphs of the kind we looked at. You also might be able to start with some things in these boxes and improve them by learning additional. Like for example, that you may have a certain action model saying that when I try to lift the box, the bottle will be airborne. That may be, it won't be on the table. Except that I do it like 3 times, and 2 times I am able to actually lift it, 1 time it falls down. So then I say, it actually looks like it will be on the table 1/3 of the time, above the table 2/3 of the time, because I just learned this by doing it. So there, you're essentially learning to improve your action model. Okay, those are sort of the hybrid approaches. There was a question. Yes.
So when it comes to like how the hybrid works versus like one or the other, I guess the thing is like kind of bouncing around in my head is, do we start with like, you said we can propagate some of the boxes ourselves and then let them learn from the base set on up. And I guess I wonder, does that approach work? Does that like kind of a blanket, or is it like specifically use the hard code in some fields and learning in others? So like with language, maybe it's better than the hybrid approach of telling like lots of we need hard code. Is the hybrid approach like not just like for one niche, but more of a general idea for like we hard code some parts of the AI and then learning the other parts? Does that make sense?
That's the slide when I get to that answer to your question. Right? But please understand, what I'm doing is I bought this anti-fogging things. You guys are just sitting and listening to me. I'm talking and exhaling all the time, and so I'm fogging my glasses. And I bought these anti-fogging things, except I'm exhaling so much that it's still not working after a while. But so it's a very good question as to how much to learn, how much to go from the human input. The ideologies, the ideologues. Science is human endeavor. Science has ideologues just the way religion has ideologues, and everything. Politics has ideologues. The only difference is, unlike religion and politics, in science, if one method basically conclusively outperforms the other method, people will all shift to the better method. That's the only difference. But up until then, you will be betting on your horse. Right? So I'll get to that in a second, but before that, let me just tell you 2 things. One is, if you're doing learning in a non-end-to-end fashion, there are 2 ways of doing learning. One is, tell me what the problem is, I just learn how to do it. I don't care, you don't need to know how I learned, what my internal representations are. The other is, you have me do it in a certain set of steps, like all these boxes should be there. So the learner basically tries to improve each of those boxes. This is in some sense a hybrid learning, where I can put some things already in those boxes, and the system tries to improve by trial and error. The advantage for the hybrid one is whatever it is doing makes sense to you, because it is basically trying to work in your language of the way you see the world. As you could see from that yellow bus, clearly there are different ways of seeing the world. Because this damn thing works well. Imagenet, the AI systems working in Imagenet now have superhuman accuracy. In the sense, these systems are actually better than humans, because very few humans know how to tell the difference between 200 different types of dogs. And you have to be like a dog fanatic to do that. And it turns out the Imagenet has like 200 different kinds of dogs, of the example. And these machines can figure out exactly which dog is which. extremely impressive. They're better than us. But then, if it does this one thing, say, yeah, looks like a good ostrich, why don't you write this? You are never going to believe it again. You're never going to trust it again. You understand what I'm saying? Our failure modes is what our trust on each other depend on. Right? I mean, I actually have in the exam, and you will see this, when I have exams, I normally have true false questions. False questions are easy. 50% you are likely to be right. You toss a coin, you put a true or a false, you'll be right. But there's a trick. In my true false questions, you have to give a justification as to why your answer is right. I read it. And my thing is, even if you gave the right true false answer, if your justification is wrong, you get 0, maybe negative. If on the other hand, your justification tells me you're thinking it along the right lines, but you essentially did true false wrong, I trust your judgment. This is what we do. This is how we trust each other. Our failure mode change the way we trust each other. Do you understand what I'm saying? So that is a very important thing to keep in mind in terms of the ostrich kind of an issue. Anyway, so this is about the learning. I think so. There was a question in the very beginning. Who is the guy who asked that question? When is supervised learning coming? Who is the guy? You? Wow. Okay. So I think you understand now. It's a lot more complicated question. It's not just when is it coming. What is it learning? Do you want to know what it learned? Or do you just want it to be right? Part of the reason the whole thing that's playing out right now about Tesla, how many of you have Teslas, autonomous driving cars? Okay, so you should come more often to office hours. I might want to drive your car. I can't afford one. But anyway, this is the thing about Tesla, right? It is a pretty good, reasonably good autonomous driving system. But I don't know how many of you follow the news about Tesla. Like the other day, there was this tragedy, this great case where it thought that a white truck crossing the street was part of the sky. So it basically let the car go through, and this other guy was fiddling with his iPad just like me, and so he was under the truck and he died. And more recently, somebody who did not die because essentially he was also keeping track of what the car is doing, lived to tell the tale that basically, I forget the exact thing, but it confused the moon in the sky. What did it do?
He kept looking at the moon and saw the yellow light.
Yellow light. The moon looks like a yellow light. I mean, how many times have people just not moved because they've seen the moon? Those people don't exist because people behind them just sort of kept pushing them away, right? So when these kinds of things happen, wow, it's doing well, but oh my God, once in a while it thinks the moon is a yellow light. And there was in the very beginnings of Waymo, Google car, it wants a plastic grocery bag flying in the air. Because because cars go and the plastic grocery bag was left on the street, so it flew into the air. This car thought it was a flying deer. This is transfer learning, zero-shot transfer learning. For those of you who know, you can take credit for it, I guess. It looked like a deer. I was flying, but if you do the action for that could be very bad. And it's because the system is not looking at the world the way you are looking. So we celebrate when systems do the same successful thing that we do, but the real question is what happens, do they fail the same way we fail? And the failure modes nobody thinks of. Normally you try to just increase the success, but the type of failure tells me whether I should be able to trust the system or not. And that ultimately is the reason why you need to think of whether or not you want an end-to-end learning or whether you want to go through some middle ground where humans can still debug if required. And they can make sense of it. The interesting thing is, this is a lecture. I've been teaching this class for forever, and this is a lecture I have to do it only nowadays. Because in the past, as I said, everybody agreed that it's like you program the agents, you program the intelligent agents, just like you program your parting algorithms. And so the real question is, once you put all the things in each of them, then how do you put those pieces of knowledge together to make decisions? Now we have these alternatives, and they have different trade-offs, and you have to decide which one to use them. Okay? The other thing I wanted to show is this, that it looks, I know that at least somebody said, I thought we already figured out the intelligent agent architectures by the first class, why did you even waste time in the second class? And that person must be really mad at me because I'm spending one more day on the third class too. Let's just get to it already. But the point is, I want you to understand not just how to do one algorithm, but where the field is. Do you understand what I'm saying? You will learn some algorithms, but you also know where the field is as a whole. Okay? And so these are two talks from each side that I was talking to you about. One was Yoshua Bengio giving a talk day before yesterday. And he's still not completely clear whether we should just go for end-to-end learning, whether we allow humans to give anything, or should just machines learn from scratch everything. The other is, like, for example, Feifei, who is fine with having a middle layer which makes sense to humans. If people giving invited talks at each guy can't make up their mind as to which is right, it's because it's not clear which is right as yet. I want you to understand. That would be the difference between you and somebody who reads some New York Times or some other clickbait article and says, oh, it's all learning, or it's all inference, or it's all some random thing. It's the nuance that is important. Okay? The other thing that I wanted to, and I said, you're living in interesting times. I mean, if you took this damn course 6 years back, it would have been something simpler. I didn't have to I used to have only 2 classes for intelligent architecture. Now it's become 3. Because I need to make sense. I mean, I am one of those people who wants to make sure that there is a reason why I am teaching you this topic. And for every topic I teach, I have to be able to connect it to these 2 lectures. As much as they're frustrating right now, as the semester goes, you can come back to this to make sense of why is routing this particular piece or this other particular piece. Which of the ideological, which side of the ideological divide is making sense. Okay? Okay. So, couple more things on this. So this one actually is almost worth reading, so I'll more or less try to do this, but essentially the answer to how much human written and how much learned is that typically people start on the 2 extremes. It's easier, and then they hope to try come in the middle. In fact, you heard Yoshua 4 or 5 years back, he was way to the other extreme, saying it's just end-to-end learning or nothing at all. Now he talks about system 1, system 2 differentiation, and maybe there are symbols, but the system learns the symbols. Okay, so ideologically there are 2 different ways in which AI has progressed. One is inference focused, where you start by assuming that the models are available, and the state representation, action representation is available to you. These work exactly in domains that are human designed. For example, games it will work, web agents they will work. Or if there is a simple way of converting the sensory information into objects, or Feifei's work is working, that may also work, but that didn't work at that didn't exist that time. Basically, the inputs were already in symbolic form about the world state. Right? By the way, if you're playing chess, think about it this way, it's the same thing. If you're playing chess, what do you see on the board? you actually see pixels on the board. But your mind directly converts them into symbolic representation. You understand what I'm saying? Before you played chess, you already knew how to make differences, how to differentiate between the shapes of the chess pieces. 1997, Deep Blue won over Gary Kasparov, ending the human dominance of chess. Because from then onwards, machines are better than humans. The interesting thing is Deep Blue can't tell a piece one from another piece if they came and between. It can't recognize pieces. It doesn't understand shapes. It's not looking at the board that you are looking at. You look at the board and quickly convert it into a symbolic representation, and it's the same symbolic representation that somebody is giving to the system. And you can play chess in that symbolic level, which is why chess is a cerebral game. You don't really need to have eyes to play chess. You agree to that, right? How many of you know Blitzkrieg? Blitzkrieg is a form of chess where you are not shown the board. And you still have to play. Because you know the initial state and you just have to figure out where it would be. You know, it's like walking in your home when no lights are on. You can do it fine in your home. If you are in your friend's home, you have a harder time because you don't know the layout. What do you do, by the way, if you are in your friend's home, you wake up in the middle of the night and you don't know, it's pitch dark, and you need to go to the bathroom? How do you figure out where to go?
Wake up the friend.
You can wake up the friend, yeah, that's always possible, but what do we do?
Turn on the light.
I said, okay. Imagine there's a huge 50-watt electricity failure. Yes? None of you basically never played hide and seek with, basically walking around with eyes closed. The way you would localize yourself is by using the walls. So wherever you are, you try to walk in one direction straight because you have this meta-knowledge that rooms end and there are walls at the end. So when you hit the wall, you follow the wall. And you know that normally bathroom would be some kind of a hole in the wall. And then you pass through it. This is what people do. It could. And then you'll have to again, use touch to figure out. All sorts of problems can happen when you touch improperly. But the point is that this is how you try to deal with lack of sensory information. So somebody mentioned Helen Keller in the last class. So there is this sort of mean joke about Helen Keller, that what would her mother do when she's mad at Helen? She will put her in a cylindrical room. It's a mean joke, right? Basically because the wall essentially is cylindrical and so you can't tell, you can't localize yourself. Okay, anyway. So coming back to this, so the state representation, action representation are there, you focus on the inference in the context of the model, and you sort of make a promise to yourself that eventually you'll start looking at the learning part. So the original way intro to AI would be taught would be this way. We would tell you how to, if I give you the knowledge, how to put them together, to do search, to do planning, to do probabilistic reasoning, etc. And at the end of the course, we'll do some machine learning stuff about how to learn to increase the amount of knowledge you have with these models. Okay? Postpones learning, reasonable for explicit knowledge domains with good models. Chess, Sudoku, vision planning, web programs, web shopping agents, etc. AI development followed this direction for much of its history. Okay? Then the learning focus, assume that the agent doesn't have any a priori models, like nothing at all. This is the other extreme. Okay? Focus on learning even primitive models representations, typically reflex agents. This is the kind of thing that you're doing when you're trying to figure out whether it is a school bus or an ostrich. Right? And it basically has no common vocabulary with you. Promise of eventually getting to inference. So Jan LeCun, who is actually the guy behind Conway, once in a while he says, we're going to do planning too one of these days. Because he's coming from the other extreme, where he made vision work well. And the people on the other side, would say, we are going to do vision one of these days. Because we're figuring out already how to do plan. And for the full problem, you need to do both. And for certain kinds of domains, this approach would be better. Certain other kinds of domains where, for example, it's a one-shot decision, for example, figuring out what is the type of the animal in front of you. Vision is fine. Like this kind of a reflex architecture is fine. Okay? And then this whole thing is, and then this typically postpones inference. It's reasonable for tacit knowledge domains with no good models, but a lot of examples and experience generated. That's what we have been doing now for some of these vision tasks. And this sort of puts in perspective this big distinction I was trying to make in the earlier meetings between tacit versus explicit knowledge. Okay? And really you need both. And I hope this class sort of convinced you that these are really two extremes and you need to understand how to put them together. Because all the action is going to be in the middle. But the only thing I can teach you right now is pieces from both ends. Okay? So, for a couple more things. So, tacit versus explicit knowledge, I hope I said enough about it, but there's a slide on that. Once more, you can look at it. This Polanyi's paradox you read. I also made you read this directionality of the way AI developed. One other thing is system 1, system 2. I brought this up. There's a slide. You can read this. I kind of mentioned system 1, system 2 before we came here in terms of this is sort of a metaphor for how human brain works. But even though they are connected to tacit explicit, they are not one and the same. In fact, things that you have explicit knowledge about, sometimes you might reflexively do it after a lot of practice. This was the example I gave last class of you know how to do derivatives from first principles, but you memorized something like log x is 1 by x. But if I question your judgment, you can prove that you are right by going back to first principles. Whereas if all you learned is, I looked at Google, it said dy dx of log x is 1 by x, that's not an explanation that you are right. Okay? So that is the other thing about system 1, system 2. I basically, one thing that I want to show you, so the plan of action for us for the next 2 weeks, when we come back, is we'll start with the inference focus and interleave learning slowly. So first we'll look at atomic representations, basically state representations, and then if I know the state and I know a way of going from state by doing action to another state, I can put these actions together to find a path in a graph. And that would be one form of doing, collecting actions. Those would be called search agents. We will look at how search agents work and go from there slowly into more generalized form of search, which actually gets you to Markov resistance processes and reinforcement learning. And after that, we will get back to supervised learning. So with respect to people's question of when will I do what learning, we will do reinforcement learning way before we do supervised learning in this class. Okay? So that's sort of the outline of what we'll be doing next 2 classes. When we come back, we'll start doing problem solving. Okay, thanks.